Good morning. Today I am presenting one artificial intelligence component within the Hidalgo project, namely a route pruning algorithm for automatic location graph construction. This component was developed in a joint collaboration between the Node Center, the University of Stuttgart, and the Brunel University in London. At first, I want to give a very short introduction into the migration use case and also a short introduction into the topic of graph pruning. Next, I want to present the components and give some examples and visualizations, and in the end, give a short summary. The migration use case in the Hidalgo project deals with the simulation of forced migration, which is being executed with agent-based models. And some of the goals of this use case are, first and foremost, to save lives by supporting NGOs and governments, then also to complete the data collections on refugee movements, and also to investigate the consequences of border closings. For the use case, necessary input is a graph structure. And in this graph structure, the nodes correspond to physical locations. The edges of the graph correspond to the direct routes, and the edge weights correspond to route distances. And with that, we get a so-called location graph. These location graphs have been created manually, which is a very time-consuming and error-prone process. But with our component, we can now automatically create these graphs in a very short time. And next, I want to give an introduction into the topic of graph pruning. First of all, a graph is a tuple that consists of a set of nodes, which we denote by L, a set of edges, which we denote by E, and the corresponding edge weights. And here we have a graph on the left-hand side with in total 6 nodes, and an edge here, the edge AB, for example, has an edge weight of 1. Up next, a path. What is a path? A path is basically a set of unique nodes where each node is connected to the one before it. So as an example, the path BAEF here, and the distance of this path is just the summation of the individual edge weights, which in this case is equal to 4. As you can see, there are several other paths between the two nodes B and F, such that we define the set of paths between two nodes. And here, for example, as mentioned before, the path P from the slide before is part of the set of paths between B and F. Up next, I want to introduce the concept of pruning. And pruning, or in our case, graph pruning, basically corresponds to network simplification. We want to simplify this graph by removing edges that are not necessary. And in general, pruning is trying to find the smallest graph, which we denote by G star, such that the distance of the path between two nodes in G, that the shortest distance of the path between two nodes in G is equal to the shortest distance between two paths in the graph where we have removed edges. And this condition must hold for all node pairs of L. In our case, we now want to try and see, can we remove this edge between the two nodes B and F? And for that, several different approaches are existing. The first one being a global strategy, where for each node pair in the set of nodes, we try to find the shortest path distance between the two nodes. And if the shortest path distance between two nodes is smaller than the direct connection between two nodes, then we can eliminate the direct connection between two nodes. In our example, we have this edge between B and F, which has an edge weight of 5, but there's also a path B, A, E, F, which has a path distance of 4, which is smaller than the direct connection, such that we now can remove this path from B to F. There are two different strategies out there for the global strategy, iterative and static. And the iterative strategy basically removes edges instantly when it finds an edge that can be removed, whereas the static strategy tries to find edges and then removes them all at once after going through each node pair. The second strategy is a triangle strategy. And here we now have that we are not looking at every path between two nodes, but we are only looking at paths that are basically corresponding to a triangle where we have only one intermediary location. And here the same holds that if we find a triangle that has a shorter path distance than the direct connection, then we can remove the connection from the set of edges. In our case, we have that the distance between the two nodes B and F is equal to 5, and we only have one triangle of connections B, C, F. And when we are calculating the path distance of the path BCF, it is equal to 6, and therefore the edge from B to F would not be removed. So we see that with the triangle strategy, we have edges remain in the graph that would be pruned in another approach. So now that we introduced the two approaches, where we have approach 1, the global strategy, it is optimal, but it is computationally expensive. And the second approach with the triangles is computationally efficient, but it is suboptimal, as we have seen. So now the question is, how can we unify the two benefits from those approaches, having an optimal computationally efficient strategy? And for that, we have additional assumptions. The first one being that the graph G that we are operating on is complete. And the second condition is that the path distances satisfy some triangle inequality, which means in our case that when we have a path like the one defined between two nodes U and V, that there exists one vertex such that it holds that the distance between the triangle is smaller or equal to the distance between the whole path. And with those two assumptions, we can develop a triangle strategy that is computationally efficient and optimal. Second enhancement of our algorithm is the introduction of a tunable pruning parameter beta. And what this pruning parameter does is it takes the sum distance of the path and multiplies it by this parameter beta. And there we have the choice to either set beta to above 1, which will end up with more redundant edges, or when we set beta to smaller than 1, we are basically loosening up our approach and giving it a bit more flexibility. Next, I want to summarize what we just had and show our route pruning approach for location graph construction. So at first, the input into our algorithm is a list of physical locations with their GPS coordinates. In the first step, we are computing the fastest driving routes between all location pairs with the open source routing machine. Now we have a complete graph, and it satisfies the triangle inequality. In the second step, we are doing the graph pruning. So we are removing indirect routes from this fully connected graph with the triangle inequality. And this will then give us as output the location graph of direct driving routes. And next, I want to go into a little bit more detail how the route pruning algorithm functions. And here we have, as mentioned, as input, the list of locations, the driving distances between those locations, and also a complete graph. We are also choosing a cutoff parameter beta for the pruning. In the first step, we are creating a copy of the list of edges so that we are operating on the original graph, but doing a pruning on the copy of the list of edges. And what we are doing then is we are iterating through all 3 tuples from L, and we are looking at each edge and set the longest edge apart. And now the pruning condition, which is step number 5, is the following: that if the distance of this individual edge is bigger than the sum distance of the 2 other edges multiplied with the pruning parameter beta, then we are removing this edge from the copy of the fully connected graph. And when we have iterated through all 3 tuples of nodes, we get a pruned graph that we denote as G star, where we have now a reduced number of edges. And next, I want to show some of the examples that we have where we have tested our algorithm on. The first example is a region in the federal state of Styria in Austria, where we have in total 15 locations. In the first step, we are creating the fully connected location graph, where we can see here in the background in blue the suggested fastest driving routes, and with yellow the connections between all location pairs. And here in this case, we are only operating on the undirected graph, but the algorithm also functions on the directed graph. In the next step, we are applying our route pruning algorithm and prune indirect edges from the graph. We have applied it with beta equals to 0.9, which gave us this graph as a result, where we see we have a major reduction in driving connections between the locations. We have also applied the algorithm with beta equal to 0.95, which will give us more locations that are being left after the pruning step, which looks like this. So in this case, we have 4 more direct driving routes between the locations than over beta equals to 0.9. In total, we have applied our algorithm on 4 different regions of different size and road infrastructure, 2 regions in Europe and 2 big regions in Africa. We've also applied our algorithms with 2 different values for beta, one time 0.9 and the second time 0.95. And in this table here, we see the amount of locations that we have. GT stands for the ground truth of direct driving routes, which is basically the manual creation of of the direct driving connections. And the next column, algo, is what the route pruning algorithm has returned. And in the last column, the F1 score, we see the performance of our algorithm, where we see that in 3 of the 4 regions, we reach results exceeding 0.9. And in the 4th region, we are also getting results for the F1 score above 0.7, which also gave us interesting insights into the algorithm to see where we could still improve it. And next, I want to show some of the visualizations we created. Here we see the comparison of the direct connections that we detected and the connections that were detected by the pruning algorithm as the dashed line. And here in the region in Austria, we see a nice overlap of the direct driving routes and the routes that were detected by the pruning algorithm. And here's also the result for the Central African Republic, where we see that even in this very big region, where we can see here already a distance of 443 kilometers, that we also achieve a really nice overlap of driving routes and actual driving routes. To summarize our findings, we developed a computationally efficient route pruning algorithm to create these location graphs. And also we introduced a tunable pruning parameter such that the results can be customized. For example, when you want a location graph with more direct driving routes, you increase the pruning parameter beta, and when you want a more sparse graph, you decrease the pruning parameter beta. We saw in the analysis of the results that long route distances can be a bit problematic, and also when 2 locations are relatively close together. But overall, we achieved really good results in the 4 regions of different size and also different road infrastructure. We've also published our results under the title A Route Pruning Algorithm for an Automated Geographic Location Graph Construction, which has been submitted to scientific reports.